we'll be at CDPR in Vancouver in June. Another very nice location. Hope to see you there. So I'll just wait till. Okay. Yeah. So I think one of the goals of this workshop, as Jamie said, was to try to evaluate the generalization ability of current monovision algorithms, but also to try to understand how current monovision algorithms, monodepth algorithms, compare to how humans extract depth information from single images. So that's what I'm going to focus on, at least in the first part of the talk here. Oh, sorry, I've got another problem. Just one sec. There we go. Maybe that'll work. There, okay. So yeah, so let's talk to start about human vision and how humans like you and I can estimate depth from a single image. So this has been studied for many decades, as you know, and the program of research has really been to try to both understand the physics and geometry and statistics of 3D scenes and how they project to planar images, and then try to understand how the brain makes use of knowledge, implicit knowledge of that physics and geometry to estimate depth from image features. And one of the main observations is that the physics and geometry really changes depending upon what kinds of features you're talking about. So whether that's shape from shading or depth from shadows, shape from texture, occlusion cues, linear perspective, and so forth. So when we look at this body of work, we really see kind of individual investigations into the different physics and geometry of each of these cues. And also something I think that's equally important is the question of how depth information is represented in the brain. So in computer vision, we seem to have kind of settled on the idea of a range map and as a convenient representation, but it's, I think, definitely not what the brain is doing. We don't know exactly all the kinds of 3D representations that are in the brain, different parts of the brain, but it doesn't seem to be a range map. Certainly surfaces are really important. Solid object representation is extremely important. So I think that's a topic of discussion and future research that would be should be prioritized. Okay, so let's now compare that to modern computer vision. I would say the program of research is quite different in the last 10 years. And as Ocean pointed out, it's really focused a lot on deep convolutional networks. It's really been a machine learning problem, I would argue, more than a vision problem. On the positive side, it's generated some really exciting results and useful systems. But I would say in trying to relate this to biological perception of depth, it's quite challenging because these are very high dimensional systems, and it's really hard to relate what these systems are doing to the physics and geometry of those individual cues that I talked about in the previous slide. So it's kind of a challenge to, I think, bridge this gap between human monocular depth estimation and computer vision. So what I want to do in this talk primarily is sort of make a case for trying to, in addition to the sort of end-to-end learning approach to monocular depth estimation for computer vision, to also consider unpacking different cues. And I think that could have a lot of positive benefits, one of which would be we could probably better understand the relationship between these computer vision systems and human depth estimation. I think there are lots of other benefits that we could gain from this approach. I'll just list a few here. So basically what I'm trying to argue is to try to understand how we integrate more powerful inductive priors into these learning systems. And the benefits would include, as for any relevant inductive prior, potentially lower data requirements. So Urshan did a nice job of covering various issues of data that limit current systems, potentially faster training, lighter models, and better generalization. So again, that's something that came up in the previous talk, that models tend to overfit their data sets and then often don't generalize that well. If we can identify more universal geometric priors, this could certainly help to improve generalization, improve reliability. Also, incorporating more explicit models of geometry and physics might help us to estimate uncertainties, kind of estimate what we don't know, put confidence bounds on depth estimates, which is very important for performance critical applications. Of course, explainability is also important for applications where performance is critical, like driving. But I think the big one for me is just scientific curiosity. I'm primarily a vision scientist, not a machine learning scientist. So I actually want to know, what the connections are between the physics and geometry of the world and image features, and how an intelligent agent, whether it's a human brain or AI, can use those image features to estimate depth. I kind of want to have a more explainable model for that as a scientist. So that's kind of my pitch. And what I'm going to do from now is, with that in mind, try to talk a bit about human perception of depth, a few things we've learned, and then try to give some examples of how, inspired by those findings, we can create useful computer vision algorithms. Okay, I'm going to start. I'm going to talk about both natural environments and built environments. I'm going to start with natural environments, which are maybe the most interesting in some sense, because we know less, I think, both actually on the human side and on the computer vision side, of how to estimate depth in natural environments. And that was indeed one of the motivations for this workshop and for the creation of this, the original creation of this data set called the SYNS data set, that was created in collaboration between University of Southampton in the UK and York University in Canada. And this data set consists of these high resolution, high dynamic range spherical images taken with a spheron camera here. And these are coupled with very carefully registered spherical range data that are captured from the same nodal point. So there's 69 scenes in this data set. 12 of those are indoor, the others are outdoor. And one of the things that distinguishes the SYNS data set from prior data sets, 3D data sets, was an effort to sample scenes more fairly. So in prior data sets, these had really been kind of samples of opportunity, right? So research teams took their kit out onto the campus and kind of moved it around to places that they could get access to, and took recorded some scenes. But of course, this could strongly bias the statistics. So for SYNS, what we did was to find a region of, I think it was 100-kilometer diameter around Southampton University, so a fairly large geographic area, and then worked with geographers to identify the 19 land use categories that were within that fairly large region. And then we sampled 3 scenes from each of these 19 categories, sampling uniformly and randomly from that geographic disk. So it's certainly not perfect. So obviously Southampton doesn't look exactly like Hawaii, for example, but although that might change with global warming. I think it's an improvement on prior work. So we hope that this data set is kind of useful in the sense that it's quite broad and fair sample. So that generated a roughly even split between natural and built environment scenes. And let's focus first on the natural scenes. So this is an example of a natural scene from the SYNS dataset. So we're just taking a planar projection here from that spherical image. And since we don't know a lot about depth perception and these kinds of natural scenes, monocular depth perception, we decided to do a very simple psychophysical experiment. So subjects in this experiment are sitting in front of a display and they see an image like this, and they have one eye patch, so they're just looking at this monocularly. And that eye is positioned in the correct location, so it's essentially replacing the sphere on camera. And so everything is prospectively or projectively correct. And then we simply highlight 2 points, as you can see here, these 2 pink crosses here. And we just ask the observers, which point do you think is closer to you? It's an ordinal judgment. Then, of course, we can ask the same question to various deep network systems by probing the range maps that they return. Okay, so what do we find? So this is an example of our data. So I'm plotting proportion correct here as a function of the difference in depth between the 2 points that we're showing the observer. And this is for a mean depth of 20 meters. So we've tested many different mean depths. We have a lot of data, but let's just use this as an example. And so, for example, for a depth difference of 10 meters and a mean depth of 20 meters, that would mean that the close point is 15 meters from the eye and the far point is 25 meters from the eye. Okay. So what do we find? So we see that as we increase the depth difference, performance gets better generally, which makes sense, right? And humans are not bad. So human performance is shown by this bluish curve here. But the models, you can see, interestingly, range a lot in performance, right? So there are some models here which basically can't do the task at all, but there are some models up here that they're not as good as humans, but they're certainly able to make an ordinal judgment here. And I want to emphasize that this is really a test of generalization, right? So these models were not trained on the SYNS dataset. They were trained variously on Kitty or NYU2 or Make3D, as you saw in the previous talk. And so what you can see here is an example of the challenge of generalization from these datasets to the SYNS dataset. As I said, humans generally outperform these network models. But there's one model here that seems to be better than everybody, especially for these smaller depth differences. So what is that amazing model? So this is what I'm calling elevation-only model. And that turns out to be just the very simple rule that whichever point is higher in the image is further away. Okay, so it's a sort of a trivial algorithm. And so it's kind of shocking that both humans and the networks are just simply kind of getting in the way of this very simple rule, right? And as a result, performing worse. So why is that rule so powerful? So as you probably know, it's largely because of the ground plane. So if these points are projecting from the ground plane or points or objects near the ground plane, then of course, if the points are closer to the observer, they'll project lower in the image, or they're further away, they'll project higher in the image. And this turns out to be very true for the SYNS dataset below the horizon, at least. So here I'm plotting log depth as a function of elevation. You can see below the horizon there's a very lawful relationship between height in the image or elevation and log depth. So given the strength of that Q, a very simple Q, it's interesting to wonder whether humans and these models are making use of that elevation Q. So to test that, we can measure what's called a decision variable correlation between humans and these networks and this Q of hires further. And this DVC is just a measure of correlation that factors out overall performance on the task. Okay, so it's an unbiased measure of correlation. And what we see is that, yeah, humans are very reliant upon this higher is further Q. with correlations ranging from 0.8 to 0.9. They don't use it perfectly, that's why they perform worse. The networks, interestingly, range quite a bit in how much they're making use of this higher is further Q. Some of the networks don't seem to be using it at all, but some of the networks are using it a lot, not quite as much as humans. Now, for human vision scientists, this is not a real shocker. This really is consistent with decades of research going back to J.J. Gibson and his ground theory. So we've known for a long time that the ground plane is a really important determinant of how we perceive 3D scenes. This is kind of just a quantitative confirmation of that theory. So given the strength of that Q, it makes sense to repeat the experiment, but now clamping the height of the 2 points so that we can no longer use that height cube. And what we find then is, of course, that systems get a lot worse. So some of the networks get completely knocked out. So you don't give them the height, then they just can't really say anything about the relative depth of these points on the SYNS dataset. Humans certainly get much worse, although we're still able to do something in this task. And there's some of the networks that are still seem to be doing something, although performance is not particularly good. Okay, so certainly haven't solved the problem of monocular depth perception in natural scenes. I guess if you had to sum up this work so far, it's just that it's a hard problem, right? But we certainly know that the ground plane is an extremely important cue that's used by humans and to some degree, some deep models. Humans are outperforming the deep models on this generalization task. Okay, so that's all I want to say about the natural environment for now. I want to move to the built environment, which is certainly closer to what computer vision research has focused on. And that's makes sense. There's a lot of important applications in the built environment, and there's obviously stronger regularities that we can exploit. And in particular, I think it's generally true that even above the ground plane, there's a lot of regularity in the form of largely piecewise planar surfaces. And I'm going to argue that this really is a very powerful regularity that I think we could make greater use of in computer vision. And for the built environment, I really think that we should think about depth perception not in terms of range maps or point clouds, but in terms of surfaces, probably for this reason. So, so let's talk about 3D surface perception. So in human vision, there's been lots of work on the perception of the orientation of 3D surfaces from a single image. So to characterize 3D surface orientation egocentrically, we use two variables called slant and tilt. So slant is just the amount a surface is angled away from the view vector. So it's just the angle between the view vector and the surface normal. Whereas tilt is really the direction in which that normal is angled away from the view vector, okay, when projected onto the image plane. So here's an example with two surfaces with the same slant, 45 degrees, but on the left, the tilt is in that direction, and on the right, tilt is in that direction, right? Okay, so that characterizes the egocentric orientation of the surface. And we're going to try to understand the statistics in terms of this polar plot, where slant is the radial axis and tilt is the polar angle dimension. And you should think of these plots as being like a concave hemisphere that you could walk into, okay? So points in the middle are the surfaces that are facing you, frontoparallel. Points on the bottom are the floor-like surfaces. These are the ceiling-like surfaces at the top. And at the left is the left walls, the right is the right walls. Okay, so it's just a convenient way of visualizing the statistics of surfaces in the world. So if we want a system that can estimate surface orientation from a single image, it makes sense to first understand what is the prior distribution of surface orientation. So if you think the world's random, it turns out you'll predict a very broad distribution, slightly peaked at front to parallel. But that's not what we see when we look at the statistics of real scenes. So for natural scenes, the ones we just talked about, there is this very strong mode at the bottom here. And of course, what is that? That's the ground plane prior. It seems to be quite important in determining human judgments of distance. But as I suggested, for built scenes, I don't know how well this got rendered, but there's first of all, the ground plane prior is even stronger. There's also, though, a ceiling prior, if you like, or a roof prior. And there's also this important mode here, which is vertical surfaces, okay, of various orientations. And I just want to emphasize that these are very strong priors. This is a log probability plot. So these are extremely important for inference. And so any system, whether human or machine, should certainly take advantage of this prior. Okay, so we've seen some evidence in terms of 2-point depth estimation that humans and some networks might make use of a ground plane prior. What about judgments of surface orientation? So we know a bit about this from prior work. So this is a study we did many years ago. So what we can do is take planar surfaces, texture them with a synthetic texture, and then ask observers what they think the 3D orientation of the surface is. And one good way of doing that is to use what we call a gauge figure. So it's like a bullseye with an arrow pointed out of it, and observers can adjust the 3D orientation of the bullseye so that the circles seem to lie on the underlying surface and the arrow seems to point in the direction of the normal. And then we can characterize the errors that people make relative to ground truth. Okay, so I'll go through this pretty quickly. So we have a lot of data on this, but I'm going to look separately at perception of slant and tilt. And the different colors of bars, so white or gray, reflect different textures. White and gray reflect different surface orientations. So white are the surfaces that are roughly floor-like, and gray are surfaces that are roughly ceiling-like. Okay. And then we're also exploring different textures here. So for slant, it turns out that generally people underestimate slant. But what we see here is that underestimation is much larger for ceiling surfaces than for floor surfaces. And then similarly, when we look at the tilt precision or standard deviation of tilt estimation, that uncertainty is much lower for the floor surfaces than for the ceiling surfaces. So this is definitely consistent with that strong mode for floor surfaces relative to ceiling surfaces. People are just better at judging the orientation of floor surfaces than ceiling surfaces, consistent with that ecological prior. But the other thing I want to point out is that this all depends also on the nature of the texture. And so, for example, for tilt estimation, accuracy is much higher for these rectilinear textures than for these circular textures. Okay. So why would that be? So we think that is due to the profound human sensitivity to linear perspective information that is available in those rectilinear textures. So of course, we know from the early Renaissance that introduction of accurate linear perspective into paintings really transforms artists' ability to render convincing 3D volumes on a 2D planar canvas. So we know that this must be a very profoundly important cue for human perception. So of course, what is linear perspective? So it's just the phenomenon that 3D lines in the 3D world that are parallel when projected to the image will no longer be parallel, but rather will converge to a point that's called the vanishing point. Okay. And as I said, that's an extremely effective way of giving an observer a convincing sense of 3D volume. So what we think, though, for human perception is that actually we're not just really profoundly sensitive to linear perspective, but really to what we call rectilinear perspective, which is also called 2-point or 3-point perspective, or in the computer vision world, the Manhattan world assumption. So that is a sensitivity to multiple families of parallel lines, which are mutually orthogonal. Okay, so called Manhattan world because, of course, in Manhattan, you have lots of vertical lines, and then the horizontal lines are organized along orthogonal streets and avenues. So how do we know that humans are sensitive to this rectilinear perspective? So there's many pieces of evidence for that. One of my favorites is what are known as Shepard's tables. So Roger Shepard produced this example many years ago. Some of you may have seen this before, but if you haven't, I think it's very cool. So here we have two tables that are obviously completely different in their size and shape, but I can prove to you that in fact they're the same. So I can take the table top on the left, and through a rigid transformation, just a translation and rotation in the plane, I can make it perfectly fit the second table. So this is kind of a conundrum, right? So it's obvious to you that these tables are different, but yet I've demonstrated that they're the same. So how do we resolve this conundrum? So the answer is that I've only demonstrated that they're the same in the plane of the projection screen. And your brain absolutely doesn't care about that kind of equivalence. Your brain cares about what their size and shape are in the 3D world that's being rendered here. And how does your brain estimate that 3D world? It's through the use of linear perspective, in particular the angles of, for example, where the two lines of the tables meet together, whether those are obtuse or acute. And it's really hard for your brain to undo that, right? To go back and see this in 2D. So it's just a simple example of how important rectilinear perspective is to human perception. And it turns out that we actually know something from neuroscience about rectilinear structure coding. So there are certain areas in the brain, for example, the parahippocampal place area, which are known to be very sensitive to rectilinear structure. So for many years, we just thought of the PPA as being this area that's important for scene perception, underlying our ability to discriminate different types of scenes like beaches from mountains and so forth. But then it was discovered that, in fact, there are many neurons in PPA that are very sensitive to whether the structure is rectilinear or not. We still, of course, don't know exactly what the nature of the computation is to compute 3D depth from linear perspective using these neurons, but certainly the machinery is there. Okay, so that's all I have time to say about human perception of depth from a single image. What I want to do now is try to just briefly talk about a few computer vision applications kind of inspired by, by those investigations, where we can use linear perspective information to solve problems. So first, online camera calibration. So this is the problem of, given a single image in a built environment, can we use the content of the image simply to estimate the rotation of the camera relative to the environment, and possibly the focal length of the camera. So it's quite important as a sort of baseline component of many applications. So in the built environment, a good way to do this is by using rectilinear perspective. So in particular, if we can identify the 3 vanishing points, then we can use those to compute both the rotation matrix and the focal length. And as a nice side benefit of that, if we do this based upon line segments detected in the image, then we can label these line segments according to their 3D orientations. So for example, here, the red line segments are vertical, and the greens and the blues are these 2 mutually orthogonal horizontal directions. Yellow is an outlier category of oblique line segments. Okay, so it's a pretty well-known computer vision problem we have a sort of classical computer vision pipeline for this problem. So edge detection, followed by the detection of global lines, followed by the limitation of those lines to line segments, and then finally estimation of the rotation and the focal length and labeling the lines according to 3D orientation. So this is completely really not machine learning, other than a bit of probability distribution estimation. There's no deep learning here, and it works pretty well. More recently, there have been attempts to solve these problems with deep learning. And so one of the arguments I want to make here is that there are some problems where you shouldn't use deep learning, right? So I would argue that this problem is one that has such strong geometric regularities and admits solution with very reliable sort of classical algorithms. And so it's not really a great application of deep learning, I would say. So when we look, for example, at the subproblem of line segment detection, the deep learning approaches that have been used, actually, if evaluated fairly against the classical approaches, which I call perceptual grouping here, really don't perform better. In fact, they perform worse than these by various measures, such as recall. When we look at Manhattan frame estimation, this is something that's been done a bit more recently with deep learning. And these methods also do not generalize outside of their training data sets very well relative to geometric methods, even though some of these algorithms were test trained on data sets that overlap the test data set here. But they're just very, very tuned to their specific training. So here we're showing error for focal length and tilt and roll error estimation relative to these deep learning methods relative to a method we just reported at ECCV last year, we call FR. And we can see lower errors consistently for this sort of classical geometric method, which also has other benefits. So these deep learning methods are not able to estimate pan because of the nature of the training pan angle. So I think, again, it's just, the lesson is that the geometric prior is so strong that it really doesn't make sense to try to learn that from scratch. It's much better to incorporate it explicitly into the model. And the other thing I'd point out is just that if you look at the nature of the computation, the constraint of collinearity here is very strong. You want to encode that explicitly. And then to get these endpoints, it becomes a 1D search problem, which is modeled as a Markov chain and could be solved using dynamic programming. So when you go to deep learning, you lose all of the access you have to those very powerful computer science algorithms and probabilistic models. Okay, so that's one example where I think, classical geometric methods are quite important. Maybe I'll skip over this for purpose of time. The second application I want to talk about is road segmentation, in particular generalization or domain shift. So this is an important problem for autonomous driving, of course, and the challenge is just the huge domain shift we have as we move from data set to data set, depending upon jurisdiction and weather and so forth. So one of our observations here was that we can divide domain shift into two kinds of shift. One we might call appearance shift, which would include things like weather and lighting. But a second important type of domain shift is what we call geometric domain shift, which really arises from differences in camera placement and the intrinsics of the cameras. And I would argue that for appearance domain shift, that is a very good target for deep learning. It's very difficult, it's very complicated, difficult to model. But geometric domain shift, I think, is something that admits more classical solutions. And so that's what we focused on in this work. So the main idea was to define a virtual camera, and then to use that virtual camera as a means to align the data coming from different data sources into a common geometric coordinate system. So basically what we're doing is taking images, physical images taken by physical cameras, back projecting to the road plane, and then reprojecting to this virtual camera. And what you're seeing in this image here at the top is the reprojections of those physical cameras. And you can see that there's quite a bit of diversity, geometric diversity in these data sets. And it's very important to account for that diversity if you want to have good domain transfer. So based upon that, we developed a pretty simple method for training a network in which for each of the images, we assume we have labeled vanishing points for training. And we use the known camera parameters and these vanishing points to reproject the images to this virtual camera image, as I described, together with the ground truth. There's a problem in that we're missing information because these physical images don't fill the virtual camera frame. So there's a process we call projective completion, which completes both the input image and the ground truth within to fill the virtual image, and then that allows us to use these data from diverse data sets to train a network. And then at inference, so just one description of the projective completion. It's a very simple idea. The idea is just to extrapolate the colors of the image along rays from the vanishing point. Okay, and that's kind of a heuristic, but it turns out to work pretty well in terms of stabilizing the training on the network. We do a similar thing for the ground truth. Okay, so the inference, it's the sort of same pipeline, except of course we don't have ground truth vanishing points. So we have an online algorithm that will estimate the road vanishing point and allow us to reproject the test image and estimate the road mass. And it's pretty simple, but surprisingly generates a huge boost in generalization performance. So this is a leave one out kind of evaluation where we train on 4 data sets and leave out a 5th data set. And you can see a boost in performance of about 9% relative to, about 10% relative to state of the art. Okay, so I'm a little running out of time, so I'll just quickly mention this third application domain, which is architectural reconstruction. So again, this is targeted at Manhattan kinds of buildings. So we're certainly not trying to solve the general molecular depth estimation problem, but the fact is that our built environment does contain a lot of these kinds of buildings, and this is a important potential application. So what we're trying to do here is just really make use of this fact that camera parameter estimation using linear perspective delivers as a kind of a side benefit the orientations of these line segments. But we don't, of course, have the depths of these line segments. So they're really just like a cloud of line segments. So what we want to do to estimate the 3D shape of this object is to try to figure out how to connect up these line segments into a graph, okay? And that will allow us to estimate an object model. So we again have a classical computer vision pipeline for this, which relies upon perceptual grouping principles. So we first build a dense graph of these line segments, then we sparsify that using a bipartite matching rule, compute minimum spanning trees. These are like little clusters of 3D structure. So we don't know how they globally fit together, but we have little local clusters, which are form very strong constraints on the 3D model. After that, there's a process of fitting these clusters with cuboids, and then there's a global optimization stage where we try to essentially minimize the number of planar surfaces on the object. So how does that work? So this is an example. Here's ground truth. Here's the output of our system we call LS3D. And you see that qualitatively, it looks pretty good relative to a bunch of deep methods that we compared against. which tend to produce much more amorphous models. Of course, these were not trained explicitly on these Manhattan buildings. Quantitatively, this classical pipeline leads to lower errors on these Manhattan buildings. But I think the important thing is really not so much that, but the difference in complexity, right? So these deep models have tens of millions of parameters. So it's very hard to understand scientifically, whereas the L3D approach is quite explainable and has just one parameter. Okay, so that's all I wanted to say. Just to summarize, what I think we've learned from some of this work, we know that humans are profoundly sensitive to various geometric regularities of the 3D world. The ground plane is extremely important, but we think that linear perspective, and in particular rectilinear perspective, is really important for human depth perception. And we think there's a lot of potential in trying to figure out how to combine those geometric regularities as inductive priors for computer vision monodepth systems. But I guess I would admit that we don't really understand the best way of doing that. Right? So I've shown you some examples of how we think you can use geometric priors in computer vision, sometimes synergistically with deep learning, but I think it remains an open question for discussion how to do this in general. Okay, thank you.
Great, so I think we do have time for a couple of questions if anyone either here or online has them. I was precisely going to ask exactly what happened on this, so when you're talking about the non-segmentation, was that also looking just at purely lines that might also correspond to specific changes, or did they always correspond to, for example, the changes in the depth, which might align more with because again, this is one of the big problems we see in these monocular depth estimating networks, is that they do tend to struggle with predicting these shallow patterns. So I was wondering if this is something that you could use as a heuristic to try and encourage the network to predict these shallow patterns.
Yeah, good question. Do I need to repeat that question? So the question Jamie asked, I think, was in studying the problem of line segment detection, do our data distinguish between, I think, occlusion boundaries, so where depth is changing or where surface orientation is changing, versus like a texture line, which would be, just a tile of a floor, for example. And the short answer is no. So the data sets are typically used to train or evaluate line segment detection are the York Urban DB, which from our lab, and wireframe. And these are just human annotated. So they are both distinguishing Manhattan line segments. So these deep learning systems are trained to specifically predict those Manhattan segments that were labeled in the data sets and ignore other ones, but there's no distinction about whether they're occluding or not. And that is a problem. That's why these, we find that even the very modern deep learning line segment detectors that are now starting to approach performance of our geometric pipeline on these data sets like York Urban DB, they still don't work as well when we try to use those segments for camera parameter estimation. And the reason is they're overfitting to those human annotated data sets where the human annotation is not complete, right? It's not perfect annotation. Thank you.
Geometric prior is very powerful, especially in the case of good conditions like light conditions. However, in the case of very tough conditions like in dark environment, geometric priors are usually less useful, especially if it's a slam pattern.
In the case of SLAM, yeah.
So we struggle with dark environment when we use key points. Key points is one example.
Okay.
Local geometric pattern. So what's your opinion on that kind of?
That's a great question. So the question was, geometric information might be harder to reliably detect when there's less light, so under challenging conditions, and in particular key point methods might not be reliable. So that's a really good point. I guess I would argue that key point methods in particular are going to be sensitive to low light conditions, but I think that larger geometric primitives might be more reliable, right? So one of the points I want to make in this slide actually is that this this Q of collinearity is really powerful, and state-of-the-art line detection methods use huffing, right? Where you're integrating, you're accumulating evidence over the whole line to detect it, right? And so the weakness of key points is that it's a very local computation, right? So it can be very sensitive to noise. So maybe, I mean, we haven't really explored what you're asking, and if we have very low light conditions, how well do these methods work? But I would hope that by using these more global calculations, we might do better. But it's a fair question.
Cool. I think that's it for this session again. So.
Oh, anything in chat?
Yeah, we might have another.
You want to quickly? It's up to you.
Yeah, maybe we can quickly discuss it. So the question, wait, I'm actually muted. If you want, you can just read it on the Zoom chat.
Oh, I'll stop sharing. Can I see the chat with a, oh yeah, here's the chat. Okay.
Yeah.
All right. So Rich Bowden asked, you presented some geometric approaches to estimating shape depth, and at one point you made a statement that it would be silly to do it with deep learning when the geometric approach is so well understood. Apologies if I'm misquoting, but how could these be combined with deep approaches? Right. So I think it's, yeah, the big question is, how do we combine these priors as inductive priors with the power of deep learning? And basically, I don't know the answer to that question. I don't want to say that it's silly to solve these problems with deep learning, of course, because it's interesting to understand what can you learn from scratch, right? It is an interesting question. I just think it's also interesting to, identify what those principles are. And then practically speaking, it could be helpful, right? If we can, use those principles more explicitly, because it means that we won't need as much training data, maybe it'll generalize better and so forth. Yeah, I don't know quite, the answer to the question. I gave an example of how we can use geometry as kind of a guide for unsupervised domain adaptation. I could talk more about that. That was for the road segmentation problem. So that's not really a very strong fusion, right? That's just kind of like using it as a teaching signal for domain shift. But I think what I personally am interested in is the introduction of side training to coerce intermediate representations to form representations of the things we think are important, like line segments, in the pathway of a deep network that's trying to deliver a more complete range map. But that's just an idea. He has another question. I don't know. The question is, how good are humans at metric depth estimation rather than ordinal? Yeah, so we didn't look at that in the study I mentioned. It was just ordinal. People have looked at that. So for example, humans are shown an image of a scene, and then they're asked to walk to an object. And humans can be pretty good in the space of 20 meters or so. So it's kind of human scale. And they definitely make use of a ground plane. So some really cool experiments where if you just, occlude part of the ground plane, so you show it in the near field, you show it in the far field, but you interrupt it, then that systematically biases the distance that humans will walk. And it seems to be a kind of a growth process as well. So if you show the near field ground plane first, and then reveal the far field ground plane later, humans are good. If you do it the other way around, then humans are bad. So it's a very interesting way that humans kind of extend their understanding of 3D from near space to far space.